I gotta go to the Monday lecture and Wednesday lecture. And I came over here from, like.
Okay, let's go ahead and get started. I'm excited for today's lecture. I've been looking forward to this lecture for more than a year and a half, ever since I came to BYU. This is what I came to teach. Electric circuits are my very favorite topic. And if there were ever a lecture to miss, this one's not it. Okay, so I'm glad you're here. As you can see, the exam went very well. The average was 76%. I was shooting for 75 and I missed. The test had 19 perfect scores, and 55% of the class got either an A or a B. I will just speak briefly to those who didn't do well, didn't go as they had hoped. The good news is that each exam is only worth 15% of your grade. And say if you got 50% on that exam, you've only lost 7.5%. You're still at 92.5% in the A range. The other good news is that where we're going doesn't build on where we've been. Unlike in 105, where if you didn't understand kinematics, you weren't going to understand dynamics. Here we're going a completely different direction, and so you can dust yourself off and move on. Yes, sir. The final exam will just cover the new stuff that we have covered since the last midterm. Yeah. So let's go ahead and get started with a prayer. Would someone be willing to offer a prayer for us this morning? Thank you.
Dear God, Heavenly Father, we're grateful for this wonderful day that we have to come to physics and to talk about the exam. And Father, we're thankful for this opportunity to start again and learn the material and help us that we can be strengthened during our studies. And we say these things in the name of Thy Son, Jesus Christ. Amen.
Amen. Thank you. Okay, let's just launch right into it. We are going to build today a model for electric current, the flow of charge through the wires and through the bulbs and through the battery. Now, on Tuesday, we're going to build a separate model for electric voltage. Now, it turns out that one of the biggest confusions that students have when they're starting out their study of circuits is figuring out the difference between current and voltage. Some of us had difficulty distinguishing between electric field and electric force. And you know that was critical. You needed to know the difference between those things. And in circuits, this is the equivalent, okay? Knowing the difference between the current that flows through the wire and the voltage that pushes the current, okay? Now, it's not surprising that people have that confusion because our leaders have that confusion. This is a quote from David Letterman, one of our late night talk show hosts back when I was alive. I was watching near midnight, and because I wanted to see him blow up this great big 500-pound pumpkin. And he says, we're going to try again tonight to explode a half-ton pumpkin. We wanted to do it last night, but the heavy rains put the kibosh to it. It seems the pumpkin had electricity running through it. Here's how. Along the sidewalks of New York City is a metal edge. For some reason, 5 volts of current runs through the metal edge on the sidewalk of 53rd Street. Wrong or sick and wrong? Sick and wrong. Sick and wrong. I was so upset that I immediately wrote to the station and complained, and they didn't care. And then I was upset enough that I actually paid money to get a transcript of that night's talk. So let's get started. We're going to start with 3 very simple experiments. And the first one just involves one simple circuit that is comprised of a battery and a single bulb. And we're going to insert an ammeter in that circuit to measure current or the flow. And then this thing is something you haven't seen in class yet. This is a variable resistor. It's a dimmer switch. That's what you would call it in your dining room. You know, you slide the little thing, the lights go bright or dim. And right now I've got a fair bit of resistance in the circuit. And you see that the bulb, I don't even see any glow there. But there must be something flowing because I saw something change in this ammeter. You see when I put it in, it went from 0 to not 0. Okay, so there's some flow. But as I reduce the resistance in this circuit, watch what happens. Two things happen. One, you see that we get more current on the ammeter reading. And also we see that the bulb gets brighter. Did everyone get to see that? As it gets dimmer, I get a smaller reading on the ammeter. As it gets brighter, I get a bigger reading on the ammeter. Profound, profound, okay? Now, the way we say that in this class is more flow, more glow. And that's going to be the foundation upon which we build our model for electric current. And remember, when I say model, I don't mean some physical model that you buy down in the store and you put together with glue. I mean a list of rules that allow us to predict what's going to happen in any given circuit. Okay. Now, I also want you to notice that more flow, more glow is very qualitative. You know, double the flow doesn't mean double the glow. I just more flow, more glow. And you also notice that when I first connected this, there's some flow, but the glow isn't enough that I can see it, and I probably you can't see it either. And indeed, it may not even be glowing. It may be that, you know, the flow through that filament just isn't enough to even get it hot enough to glow, because that's what's happening in the filament. If you're working with, this is a Montana example, but if you're trying to work a horseshoe and get it in the right shape, you heat it up in the hot flame, and eventually it gets so hot that it glows red, and then you heat it up even more, and eventually it gets so hot that it glows white. And that's what's happening with the filament there. Okay, now let's go on. Experiment 2. With experiment 2, Clark put together this handy dandy system where I can use this battery without blowing us up. So thank you, Clark. Okay, we're gonna live. And so we're gonna start with just a single bulb. And just as you saw in tutorial, it's bright. And I represent that with these dark gold rays coming out. And then what we're going to do is we're going to add another bulb in series. And we're just going to put that up here and another. We're going to buy some shorter wires here. Now, in this setup, we have 2 bulbs that are dim, and I represent that with some rays that just aren't as dark there. And what you see there is that they're the same dim. Okay, they're dimmer than the single bulb, but they're the same. They're the same. And if we believe more flow, more glow, then what that means is that I've got a lot of flow through this one. Let's call it 5, just to have a number, you know, 5 You might want to say amps, I'll say quarts of blueberry juice per second. Potato, potato, okay? Over here, it's dim, so I've got less flow. And here I've got the same flow as there, so less flow. Now, the key to understanding circuits is to always go back to the battery first and see what's flowing through the battery. And in this simple circuit here, if I have 5 going through this bulb, I got 5, okay? Now over here, the question is, what's flowing through that battery? Is it that much or is it that much plus that much? Talk to your neighbor, which is it? Okay, let's vote. But we're gonna vote with our hand. We're voting between, is the current through that battery this much, or is it this plus this? How many say this much? How many say this plus this much? Okay, we split the class 50-50 here. Now, we don't agree on what the answer is. But I think what we do agree on is that those two bulbs are sharing the current through the battery. Do we all agree with that? We all nod your head? Thank you. Unfortunately, there's 2 ways that we can interpret the word sharing. We can share like we share a book. I read it, I thought it was great, I give it to you, you read it, it goes back to the library. Or we share it like we share a pie. I eat half, you eat half, pie's gone. What kind of sharing are these bulbs doing with that current? Like a book or like a pie? Shout it out. Did they say pie? Oh, I'm so sorry.
Their neighbor and say sick and.
What's that?
They should turn to their neighbor and say sick and.
Sick and, sick and wrong. Sick and wrong. It is shared like a book. If we think of this as a flow of blueberry juice, okay, and we take one of those blueberries and we paint him green, call him Fred. He and his friends leave the battery. We always think of conventional flow, positive charge leaving the positive terminal of the battery, and they go through this bulb, causing it to light, to make it heat up. But once they get through here, they got to go through here to get back to the battery. Remember, the dump trucks don't get used up. They just go around, get more energy and dump it in the bulbs. And so it's not just the same size current, it's the same current. It's Fred and his friends. They went through here, now they're going through here. It's the same current, okay? Just like the book doesn't get used up when you read it, we're sharing like a book. Now, what that means is that this circuit must be easier to get through than this circuit. And we call that resistance. Here I would say there's a small resistance. Here there's a large resistance. And if we go back to that F equals MA of circuits, V equals IR, okay? If we look at V equals IR, what that tells us is that with the V of the battery is fixed. That's 12 volts on this battery, okay? And so if I have a small resistance of the circuit, I have a large current through the battery. If I have a large resistance in the circuit, I have a small current through the batteries. That current through the battery changes. That's key. That's got to be in your toolbox or you're going to have a bad experience on the next midterm, okay? Now, we're going to play a game today a number of times. And I call it the black box game. And that is I've got 2 circuits, each with a black box that we can't see into. But we have what we call an indicator bulb in each circuit. And it's an indicator bulb because it's my eye into the battery. I can't see any glow in the battery, of course, but I can see this bulb glowing. And that tells me whether there's a lot of current through that battery or a little current through the battery. Now, suppose in this situation, I get a little bit of glow in this indicator bulb, but a lot of glow in that indicator bulb. What does that tell you about A and B? Which of those boxes contains the greater resistance? Shout it out. A, of course, okay? So this is the way we play the game. It's always the same. The box on the left, we're putting these guys into A and B, but I'm not telling you which box is A and which box is B. But I do know that the box A always has more resistance than box B because it's got the dim indicator bulb and B has the bright indicator bulb. So the way we play this is this box A or is this box B? With your clicker, welcome to class. We're going to use your clicker a lot today, so just keep it out. Keep it right in front of you. This one's easy. Okay. Last call. Gotta be quick. We've got places to go, people to see. Good. Okay, it's B. It's B. Excellent. And the way we reason that is that, well, A has the bigger resistance. And if I look at these boxes, it's this one that has the bigger resistance. So this one must be A, which leaves this one to be B. Everyone see how the game's played? It's going to get harder, I promise. Okay. Now, you might be tempted to say, as a consequence of this little experiment, that the bigger the R, the smaller the current. And that's going to work for maybe another 25 minutes. Okay. And if you learn this, and this is what you're carrying into the next exam, not good. You have to finish your sentences, okay? The bigger the R, finish your sentence, of the circuit as a whole. Remember, we can take that whole ugly circuit, and they're gonna get ugly, as you can see, okay? I can take that whole ugly circuit and replace it with one equivalent resistance that would give me the same current through the battery. So the bigger the R of the circuit as a whole, the smaller the current, finish your sentence, through the battery. Now, when you get complicated circuits with many branches, there's some of the current going this way, some of the current going that way, but it all has to go through the battery, okay? And so that's where we're building our model, is the resistance of the whole circuit and the current through the battery. See if your neighbor understood that. If not, you know what to do. Okay. Let's go back to our experiment, and we're going to start with a single bulb again. And this time, what we're going to do is add another bulb in parallel. And so if I add that bulb in parallel, okay, and oh, it fell down here. Ugh. Okay. Now, what we see is that those two bulbs are equally bright as each other. And also what I see is that they're the same brightness as a single bulb. Okay, and we saw that in the tutorial, did we not? Now, I represent that with the same color or same shade of gold in these little rays. Now, if we call that 5 amps or 5 quarts of blueberry juice per second, and if we believe that more flow is more glow, then I've got to have 5 amps there and 5 amps there, do I not? Now, if I go back to worrying about the current through the battery, with a simple 1-loop circuit, what goes around comes around, this has to be 5. What's that? If that's 5 and that's 5, what's this gotta be? 10, yeah, it's gotta be 10. Because if I look right here at this junction, when Fred and his friends get there, they gotta make a decision. Do I go through this bulb to get back to the battery, or do I go through that bulb to get back to the battery? Fred can't go both ways. He's gotta go one or the other. And so if I'm taking 5 amps this way and 5 amps that way, I gotta bring in 10 amps to supply that. Now, these two bulbs are sharing the current through the battery. Are they sharing like a book or sharing like a pie? Now you can say your answer. Pie, thank you, thank you. You just wanted pie, is what you wanted. Okay, sharing like a pie. Now, if we use V equals IR, what that means is whatever resistance I have in a single bulb, having 2 of them in parallel is less. Okay, this is some resistance, this is less resistance. And I can even go further than that. If they're glowing the same, I know that they have the same resistance. Now, I've had some of you in my office and you've been trying to work out these homework problems by starting with the sentence, assuming that all bulbs have the same resistance, and then you go on. And they don't. And you're saying, well, Greg, you said they were identical. You say they came from the same factory, made by the same worker on the same day. His name is Sven. How can they not have the same resistance? Well, they are identical. They act the same. But what we find is that when a bulb gets brighter and brighter and brighter, meaning the filament gets hotter and hotter and hotter, the resistance of the bulb goes up. Okay? So if I've got a bright bulb and a dim bulb, they don't have the same resistance. So I can't just plug into formulas. And that's a feature, not a bug. Because once you have formulas that you can just plug into and use your math, you stop thinking about what's really going on. And so here we're just going to be saying more flow or less flow. We're not going to say, well, that's 1.5 times the flow. No. Now, here's an exception. Because these two bulbs are exactly the same brightness as that bulb, they've got to have exactly the same resistance. And 2 paths is twice as easy as 1 path. So in this case, I can actually say this resistance is exactly half that resistance. But when I went from the single bulb to 2 in series, I had a bright bulb and 2 dim bulbs. I could say it's less flow, but I can't say half as much. Now, let's use V equals IR. V equals IR. So here, because I have less resistance, I get the bigger current. And since this is, in this case, half the resistance of this, I would get twice the current as this. Okay, let's play our game again. This box on the left, is this box A or is this box B? With your clicker, get you started now. Okay, last call. You're gonna be really quick with these clicks. Last call. Good, it's A. It's A. This has less resistance than that. Now, let me summarize real quick. What happens to the current through the battery? That's what we're always talking about, the current through the battery. If a bulb or a network of bulbs is inserted between these two bulbs. In other words, when I add something in series, what does that do to the current through the battery? And what we find is that in all cases, every single case, whether it's a single bulb, two bulbs in series, two bulbs in parallel, or a bloody fish, okay, regardless of what you stick in there in series, the current goes down. And the reasoning is threefold, okay? We're clogging up an existing path, and that increases the current. I'm sorry, I didn't say that. That increases the resistance of the circuit. Finish your sentence. The resistance of the whole circuit. And we already found that when we do that, we decrease the current through the battery. We make it harder to flow because we shove something in that Fred didn't have to go through before. And now he does. Okay? Now, the important thing to know is that it's not what we added, but how we added it. And when we add something in series, we have to break the line. We have to cut off the flow to insert the new element. If I'm drawing a circuit on the board, I have to pick up my eraser and make room for that new element. Does that make sense? Okay. On the other hand, if I add something in parallel to bulb B there in this example, what's that going to do to the current through the battery? Well, it goes up. And again, the reasoning is threefold. By adding a new path, we're adding a new opportunity for flow. And we found last day that that's going to decrease the resistance, finish your sentence, of the circuit as a whole. And when I decrease the resistance of the circuit, that's going to increase the current through the battery. Okay? Increase the current through the battery. Now, we're going to find, and this is going to be a handy thing to have in your toolbox, that there are 4 ways to change a circuit. 50 ways to leave a lover, but 4 ways to change a circuit, okay? We can add a path. And that's going to cause the resistance of the circuit to go down. And I can clutter a path, an existing path. That's going to cause the resistance of the circuit to go up. Now that's 2 of the ways I can change a circuit. The other 2 are just, make time run backwards. If adding a path is going to lower the resistance of the circuit, then removing a path is going to increase the resistance of the circuit, and uncluttering or decluttering a path is going to lower the resistance of the circuit. Now again, if I lower the resistance of the circuit, the current through the battery goes up. If I increase the resistance of the circuit, the current through the battery goes down. Check on your neighbor, do a quick buddy check. Okay. Now, again, I want to emphasize that it's not what we add, but how we add it. It doesn't matter whether I'm adding a single bulb or a network of bulbs or again a bloody fish. Anything we add in parallel, we are increasing the current through the battery. And you recognize that you're adding something in parallel if you don't have to break a line. If you can just clip on the new path with alligator clips, just as a new branch that didn't exist before, then you're adding it in parallel. Now, quick question, and this one's a good tool to have in your toolbox, a critical one. which of these networks rather, A or B, has the greater resistance? Oh, and before you answer, but wait, there's more. Let's make it a little more interesting there. Okay, so with your clicker, which of those has more resistance? Okay, last call. It's a trap. Okay, A is the correct answer. Now, you notice that not everyone chose A. We're not going to Disney World. And the people that didn't choose A are the ones that took their shoes off. You may have not smelt it, but I did. Okay, they took their shoes off. Because I know that some of us have a very complex system of figuring out resistance. They say, bulbs are bad. Oh, that one's got a lot of bulbs. So they count all the bulbs on their fingers. And then they remember, oh, but paths are good. And they've already used their fingers. So they take off their shoes and they count the paths on their toes. And then they've got some complex mathematics where they subtract the good from the bad and see whether it's more good or more bad. If you take off your shoes during the exam, bazinga, I got you. Okay. Okay. Don't do that. Leave your shoes on. It's so much easier than you're making it. What you do is you circle with a red pen. Just grab a red pen and circle the new stuff. What did I have to add to that to turn it into that? And once you've got that circle, you don't care what's in it. You never have to care what's in that circle. It could be anything. Okay? Be an anvil. All you care about is how that stuff was added to the original circuit. Did I have to break a line and shove it in series? Or could I just clip it on with alligator clips in parallel? In this case, we could add that on in parallel. I just clip it on right there, and I clip it on right there, and I'm done. And so I have reduced the resistance with all this mess, This could have been a single line with 27 bulbs in series, but it still lowers the resistance. It's like that trap door opening in the ceiling with the rope coming down. It's not a good path, but it's a new path. It's an extra path. It makes it easier for us to get out of the room. Okay? Now, let's play our game a couple more times. This time we've already used our clickers quite a bit, so we'll just shout it out here. This box here, is it box A or B? Shout it out. A. That's A. And again, I circle the new stuff and I ask, how was that added? It was added in parallel. And so that lowers the resistance. So this is B and that's A. What about this? I got two paths of, ooh, that's two paths. Which one's A? I'm sorry, is this A or B? That's what I should ask. B. That's B, okay. And again, we circle the new stuff and then we ask, how was that added? Well, that's parallel, Greg. Yes, it is parallel. But I don't care what it is, I care how it was added, okay? It's a parallel network, but it was added in series. Now I can see that by drawing. I started with a single bulb, and to add that network, I'm going to have to cut that line. I'm going to have to break, well, let me actually use my eraser. Okay, I'm going to have to break that line and shove the new stuff in. Okay. And so this one on the left is B. One more time. Is this one A or B shouted out? A mighty shout went up throughout the land.
B.
B, yeah, B. We added this bulb, or maybe that bulb, one of those bulbs, and that was added in series. And so this is B and that's A. Now, this one's a little harder, so we're going to use our clicker here. Which of those circuits, A or B, has the greater resistance? Oh, let me get you started. I was forcing you to think, wasn't I? That hurts. I'll leave a mark. Okay, get your vote in. Last call. There's 3 more of you. Maybe not. Okay. We did pretty good. We did pretty good. But a lot of you chose A. When you are comparing 2 networks to see which has more resistance, and that's one of the most common things that you do in these problems. You do it in every problem, really. What I suggest is that you draw the 2 exactly the same, okay? So I start with the simpler one, B, and I've got a bulb in series with 2 bulbs in parallel, like that, okay? That's B. And then I draw A, the same, but I'm going to draw it upside down. That's not going to change anything. Now, if those were the 2 circuits I was comparing, they would obviously have the same resistance, but something's missing. So now I take a different color pen and I draw what's missing. Did I at any time use my eraser? I did not. So I added those bulbs in parallel. But wait a minute, Greg, they're in a straight line. That's not what series means. Series means, you know, I had to break the line and shove it into an existing line. I could also draw this like that. Would that be the same circuit as A? Say yes. Yes, okay. And so clearly I have added that in parallel. So the one on the left, A, has a smaller resistance. Okay. Check with your neighbor, see if your neighbor bought that. Okay. We need a few more tools in our toolbox. One of the most important tools to put into your toolbox is the idea of be the river, okay? Just be the river. And as the river, leave the battery and go around from one terminal of the battery to the other. And it doesn't really matter whether you go clockwise or counterclockwise, but just be the river. And everywhere you come to, every place you come to a branching point, ask yourself the simple question, do I split 50-50 or some other way? So in this circuit, if I wanted to rank those bulbs, I would say all the current through the battery has to go through A. It's an indicator bulb. And then when it gets to this branching point right above B and C, it has to decide, do I go left or do I go right? Well, these are identical. There's no reason to choose left over right. And so this would get half of the current through the battery, half of the current through the battery. And so I would say that A is the brightest, B and C are equal to each other. And my reasoning would be all A gets all of it, B and C each get half. And I would justify the half by saying that B and C share equally because each branch has the same resistance. The two branches are identical. Now, if I were to compare the bulbs in these two circuits, what I would find is that A and F, the two indicator bulbs, are the brightest and they're equal to each other. And all the other bulbs are dim and the same dimness. And the point here is that it really doesn't matter the order in which these occur. That simplifies your problem, okay? I don't care whether the indicator bulb came first or last, doesn't matter. Now, another tool, an important tool. Which is brighter, bulb C or D? Tell your neighbor what you think. Okay. The tool that you put in your toolbox is the current favors the path of least resistance. And I would really, really, really like you to use favors and not chooses, okay? Because all of the current doesn't go the easy way, just more than half goes the easy way, okay? And so in this case, all the current goes through A, B the river, and when it gets to this junction, it sees an easy path through D and a harder path through B and C. And so more than half will go through the easy path, less than half going through the hard path. And so the ranking would be, A would be brightest, it gets all. D would be next, getting more than half. These guys would be equal to each other. And how do I justify this equal sign? If you were to write a sentence justifying that equal sign, and that sentence had one word or less, what would the sentence be? What one word could you use to justify that? Series. You know, if you say they're in series, they got to have the same current. Whatever goes through one goes through the other. Okay? Now, let's take this to the extreme. B the river. Which is the brightest bulb? Which is the second brightest bulb? Third brightest bulb? Rank those bulbs, people. Talk to your neighbor.
Maybe he is a bit brighter. I don't know. Shutting off my brain.
Okay. Let's do it together. B the river, all of the current leaves the battery. I don't know how big that is, but it's that big, okay? And when it gets to this first branching point between A and B, it has to decide, do I split 50-50 or some other way? Which is it? 50-50. So they each get half of the current through the battery. And then at this junction, all the current comes back together. Whatever I started with, I still have. And when it gets to this junction point, it chooses 50-50 or some other way. Some other way, more than half going through E, less than half going through D. And I drew that arrow right here instead of here and here, because I want to emphasize that this is the same current. It's not just the same size current, it's the same current. It goes through C and then it goes through D. Or maybe the other way, depending on which way you're doing your flow. But if we go conventional current, it would go that way. Okay, and then it comes back together and goes back to the battery. So the ranking, more flow, more glow, would be E is the brightest, A and B are tied for next, and C and D are tied for last. And again, I could justify this equal sign with one word, series. What justification do I have for that equal sign? Parallel branches that are identical. Okay, that's why we split it 50-50. Okay, good. Now, new idea, and I just realized that I made a mistake taking these off the board, but I'll put them right back on. This is one of your homework problems, problem 9-2. If I have two bulbs in series, Muhammad to the mountain. Okay, and just gonna put these in series. What's gonna happen if I close that switch? First of all, what's gonna happen to A, and second, what's gonna happen to B? Tell your neighbor. Okay. First of all, what's going to happen to A? Get brighter, dimmer, stay the same? Brighter. Brighter. And what's going to happen to B? Brighter, dimmer, stays the same? Dimmer and out. Okay, we're shorting it out. If I take this wire and put it from one side of the bulb to the other side of the bulb, that's the same as closing that switch. Okay, and so watch what happens. Oh, dang. Let me do that in reverse here. Okay, so there was a circuit again. And now if I short that out, bulb B goes out, but A gets brighter. Why? Well, I just added a path. Adding a path does what to the resistance of the circuit? Lowers it. When I lower the resistance of the circuit, what happens to the current through the battery? Goes up, and all the current through the battery goes through A, so A gets brighter. Okay, now, the point that this is making is that shorting a bulb or a network is an exception to our rule that we just developed. We said current favors the path of least resistance, but it doesn't all choose the path of least resistance. This is the exception. If one of the paths is a perfect wire with no resistance, then all of the current will choose the wire with no resistance. And we always assume in our homework problems and on the exam that we have perfect wires, that we don't worry about any resistance in the wire. And we find in practice that the bulbs have so much more resistance in the wires that we don't have to worry about the resistance of the wires. See if your neighbor understands a short circuit, please. Now, as a side note, by putting this wire from one side of bulb B to the other side of bulb B, I shorted out bulb B. If I bring it all the way to the other side of A, what am I shorting out? The whole thing, including the battery. And what happens to this wire? It melts, okay? And that's what happens when you've got a short in some place in your house. That's why you've got these circuit breakers to protect you from that. Because if you get a short from one side of the power supply to the other side with very little resistance, you get a huge current that's going to heat up very fast in the walls of your house and cause a fire. And so those circuit breakers are just waiting there looking for high current, and then they trip. Back when we were alive, what they did is they had a little piece of material that would melt when the current got high enough. And you couldn't just flip the switch back, you had to replace the, yes, sir.
I was just gonna ask, why does A get brighter?
Why does A get brighter?
Yeah.
Because closing this switch added a path. And anytime we add a path, we're adding an opportunity for flow. With the switch open, Fred has to go through A and B to get back to the battery. With the switch closed, Fred goes through A and he's back. Less resistance. Okay? Now. Any more questions? Okay. What we found at the end of that tutorial this week was that the current model, the model for electric current, sometimes gave us answers that were, well, they just weren't answers, okay? And that was because our model was qualitative. It wasn't providing us with numbers, it was just saying more or less. And let me demonstrate that with this simple circuit here. If the switch is closed, I know that A is going to be brighter than B and B will be equal to C. Does that make sense? With the switch open, I know a couple of things. I know that A is equal to B. They will now be in series. Everything that goes through A has to go through B, and C will be out. Is C shorted out? No or heck no? Heck no. Shorted out is when I put a wire from one side of C to the other side of C. C is out because it's on an incomplete path. And you might be saying, well, Greg, what's the difference? I mean, out's out, right? Out's out. Well, an incomplete path just means that no current's flowing over here. A short means more currents flowing through there, maybe enough to burn down your house. Your insurance company cares whether it's a short that's making it go out or an incomplete path that makes it go out. And if your insurance company cares, believe me, you should care. That's just true in life, okay? Now, the question that we can't answer is what happens to B when we open that switch? I know what happens to A. I've removed a path. If adding a path lowers the resistance of the circuit, removing a path increases the resistance of the circuit. And that means I have less current through the battery. A is going to get dimmer. But our model doesn't say how much dimmer. If A goes from that big to that big, if it just gets smaller by a little bit, then B is going to get brighter. Why? Because originally it was just getting half of the current through A, and now it's getting more, it's getting all of the current through A, okay? And 100% is bigger than 50%. But 50% of what? If the current through A gets a lot smaller and B gets all of it, it gets dimmer. And so I call this a pizza problem. If you are hungry and you are asked if you would rather have half of a large pizza or all of a small pizza, what question do you want to ask? Yeah, how much smaller is the small pizza than the large pizza? If you don't know the answer to that question, you can't choose. You can't choose. And our model does not predict whether the current through A gets a little bit smaller or a lot smaller. It's like, let's just make up a story here. JK is my son, and remind me of your name. What?
Carrie.
Carrie, my daughter. Okay, and I come to Carrie and I say, I got good news and I got bad news. Your brother JK, this was the last straw. This was it. He is out of the wheel. He gets nothing. You get it all. Okay. Oh, and some more news. The stock market really tanked today. Okay. So is Carrie better off today than she was yesterday? We know that JK's not. Okay. He's out of the wheel. But what about Carrie? her share went from 50% to 100%, but the family fortune just took a dive. So we don't know. We don't know, and we can't know without knowing some more information. Now, that more information in the case of circuits is our model for electric voltage that we will build on Tuesday. And then once we have that model for voltage with two models, we're going to be able to answer all circuit questions. There won't be anything. That's not true. I actually, when writing the test back in Montana, found one circuit that gave me a pizza problem with the current model and the voltage model. Unfortunately, I had already Xeroxed that test 350 times. So anyway, I have that problem in a special place in my desk drawer to remind myself never to assign that one again. So, but all the other problems you can solve. Okay, now I've got a circuit here on the board. And before I hook the battery up, I would like you to predict, let's label things here. This is bulb A, and this is bulb B, and this is bulb C. That right up here. And this is D, and this is E. Okay, so the switch is open. And the question is, which is brighter, A or D? Which is brighter, A or D? Talk to your neighbor about that.
The switch is open. Not going through the switch. I feel like I know it, but I still know the problem. I know.
Okay. Which is brighter, A or D? Shout it out. A. And remember what I taught you, when you're comparing the resistance of two networks, draw them the same, okay? Draw them exactly the same as each other. The simple one is D and E, and then this would be A and B. And then ask yourself, what's missing? What's not there? And it would be bulb C. And so I put that in. And the question is, did I have to add that by using my eraser, breaking an existing line, or did I just clip it on as a new path, new opportunity to flow? Yeah, I added this in parallel, bulb C. So this branch here is going to have smaller resistance than this one here. And that means that when the current gets to this branching point right here, it's going to see an easy path and a hard path. So A is going to be brighter than D. Let's see if we were right, should we? Thanks to Clark, we have the ability to just test that. Gonna hook up the battery there. Hook up the battery there. And lo and behold, we're right. A is brighter than D. Now, you'll notice that these guys are really quite dim. And if I were to ask you, is that half as bright as that one? What would you say? No. But if I were to ask you, is the current through this bulb half as much as that one? What would you have to say? It better be, because the current doesn't get used up. And these two bulbs are identical. Once it gets through this bulb, it's got a split 50-50. So this one has exactly half the current as that one there, okay? What I'm trying to say with that is that the glow is not directly proportional to the flow. We can say more flow, more glow, but we can't say twice the flow, twice the glow, okay? Be careful with what you claim, Now, the next question, what happens to A and D when I close that switch? When I short out E, what happens to A and what happens to D? Talk to your neighbor. Okay. Get ready to put something in your toolbox, people. First of all, watch D. D got brighter. Okay. Now, I want you to watch A. A stayed the same. Okay. And indeed, B and C stayed the same. Now, let me go further. If I unscrew A, did that change D? No. Okay. So if I open the switch again, making a change to this branch doesn't affect that branch. I can hit this bulb with a hammer and break it. This branch doesn't care. I can short out either of these bulbs, or I can unscrew one of the bulbs, and this branch doesn't care. These two branches are independent of each other, and that simplifies your problems. A characteristic of an ideal battery, which we will always assume, is that branches connected directly across it are independent. So the key there is directly across it. This is a branch, call it branch 1, and this is a branch 2. And you see that if I look at the connections, branch 1 has a connection that's directly connected to the positive terminal of the battery, directly connected to the negative terminal of the battery. Likewise, branch 2 has direct connection with nothing but wire to the positive and direct connection to the negative. Now, Clark has arranged to have these little bars made that we can essentially use as a wire. And so anything that's going from this bar down to that bar is going to be one of these directly across the battery branches. Now, I have some caution tape here, and that is there's two flavors of parallel. I call them vanilla and tutti frutti, okay? The fancy kind of parallel is parallel across the battery. This branch is parallel across the battery to that branch. The vanilla kind of parallel, the ordinary parallel, is B and C. You'll agree they're parallel to each other, right? But not parallel across the battery. And when I change one of them by unscrewing it, it affects the other one. These are not independent of each other, okay? But parallel across the battery is independent of the other branch. But if I turn that one off, this one cares. So these are not independent. See if your neighbor understands the difference between vanilla and tutti frutti, regular and parallel across the battery.
Parallel across the battery itself.
Okay. Now, if I were to add another bulb to that circuit, an indicator bulb in this case, and ask you to compare A and D, which one's brighter, would your answer be the same as it was before? Would A still be brighter than D with that switch open? I mean, all the current has to go through the indicator bulb, but when it gets here, doesn't it still see an easy path and a hard path? And wouldn't more than half of the current through the indicator go through the easy path? So A is still going to be brighter than D. They're going to both be dimmer than they were before because of that extra resistance we added in in series, but the ranking would be the same. Now, when I close the switch, you remember that when we didn't have the indicator bulb, this branch was independent of this branch. And closing that switch didn't change any of these bulbs. But now they're not connected across the battery. They're not independent, okay? And so when I look at these branches that we had before, I can get to the negative side of the battery with nothing but wire, but trying to go this way, I got something in the way. And so these are no longer independent of each other. Now, what happens if I close that switch? Well, if I close that switch, what happens to the current through the battery? I've added a path. The current through the battery does what? Goes up. And so that means that that indicator bulb gets brighter. I get more current through the battery and all of it goes through the indicator bulb. Well, what happens to D's share? It was getting half of the current through the indicator. I did not say that. I did not say that. It was getting less than half of the current through the battery. When I close that switch, now it becomes the easy path. And now it gets more than half of the current through the battery. So I know that D gets brighter. Its share gets bigger and the current that it's sharing gets bigger. Okay, so it gets bigger. But when I ask about, so D gets brighter. When I ask about A, I get a pizza problem. The current through the battery that we're sharing got bigger. Well, it seems like that would want to make A brighter. But A's share of the current through the battery went down. It was more than half and now it's less than half. One of those effects is trying to make A brighter and one is trying to make it dimmer. And we don't know with our model which one's going to win out because our model is just qualitative, not quantitative. And so the way we say it is that A now gets a smaller share of a larger total current. And the current model fails us. And we'll get another model on Tuesday. Now, let me help you with your tutorial homework, problem 4.3. In your homework, you had 5 networks that you needed to rank from the most resistance to the least resistance. And there's a little bit of a wrinkle in that problem, okay? And I'll show you that in a minute. Let's first of all rank these two here. Which would have more resistance, A or B? Shout it out. A, yeah, I circled the new stuff. It's added in parallel, okay? Now, when I compare these two, which has more resistance? Shout it out. E, I circled the new stuff. It was added in series, so it has more resistance. So here's the wrinkle. In the tutorial, you're asked to explain your reasoning for your ranking. And when I'm ranking B as compared to E, there's no way I can just take out my red pen and circle what's different, okay? I can't ask myself, what did I have to add to this to turn it into that? Or what did I have to add to this to turn it into that? There's too much change. And in those types of problems, what you do is you set up a straw man, okay? If I know that this has resistance R, I just made that up. I know this has less than a single bulb, and this has more than a single bulb. Now I can rank E relative to B, because I know how they compare to A. Okay, that's your homework problem there. Now, let's review the current model before I let you go. More flow equals more glow. That's how we built the model. That's how we recognize where there's a lot of flow, just to see the glow. And we want to always use the resistance of the circuit to determine the current through the battery. When the resistance of the circuit goes up, the current through the battery goes down. They're inversely related to each other. Again, it's not what you add, but how you add it. If you add something in series, you're going to lower the current through the battery. If you had something in parallel, you increase it. The next tool we put in our toolbox was current favors the path of least resistance, and that just makes sense to us. The last tool that we just put in was that branches connected directly to a battery are independent of each other. And we have no rationale for that. We just saw it with our own eyeballs. We saw it happen. We saw it in front of us. We will understand that piece on Tuesday, but for now, without a voltage model, it's just an observation as part of our model. Now, when are elements in series? Whenever charge goes through one, whatever charge goes through one element must be the only charge that passes through the other. There's no other path between them. And that means they must have the same current, not just the same size current, but the same current. Fred goes through one with his friends and then goes through the other. And you need scissors to add something. You've got to break an existing line. Or if you're working on the board, you need an eraser to erase part of the existing line. Now, when are elements in parallel? At a junction, charge, Fred and his friends have to choose. Do I flow through this one element or do I flow through the other element? They can't go through both. And we find that elements that are in parallel are connected on both sides with nothing but wire. So B and C have a connection there and a connection there with nothing but wire. So they are in parallel. But A and D are not in parallel. I've got a connection there, but I can't find a connection on the other side with nothing but wire because all of this junk's in the way. However, I can say that this network of A, B, and C is in parallel with this network of D and E because I've got a connection on this side and a connection on that side. And we can add things in parallel without scissors just by clipping the new stuff on. Now, this is a practice problem from an old exam, but we don't have time to go through it. So we'll start our class on Tuesday with this problem. Why don't we go have a weekend?